So what we're going to do now is look at drug absorption and pay particular attention to drugs getting into the systemic circulation. And our goal here is to understand these concentration versus time graphs. So the first thing we need to be familiar with is the most important equation in all of pharmacokinetics. And this is something you learned in high school. Concentration is equal to mass over volume. But let's make this equation specific to pharmacokinetics. So what is concentration referring to? Well, here we're dealing with the plasma drug concentration. And remember that the plasma is just the blood minus the cells. For the mass, we're looking at the dose of the drug which reaches the systemic circulation. So I want you to make this association. When you think of mass, you should be thinking of the dose of the drug. Remember, you give a drug in milligrams, right? I took 10 milligrams of whatever drug. So it's not just the dose you give, though. It's the dose that gets into the systemic circulation, the dose which gets absorbed. Important point. And finally, the volume. And for simplicity's sake, right now we're just going to assume that the drug is only getting in to the plasma. And so we'll only consider the plasma volume now. But in reality, we'll see that drugs actually get distributed into a larger volume throughout the body, beyond just the blood. So, just a couple of reference terms. Plasma, as we said, was the blood minus the cells. And for the average about 70 kilogram individual, the blood volume, let's say, is about 5 liters. And if the plasma consists of about 50% of the blood, that means the plasma volume is about 2.5 liters. So let's put this all together and do a question. So a 10 milligram dose of drug X is 100% absorbed. What is the approximate plasma drug concentration shortly after administration? So the first thing we do is we kind of underline the things we know. That's the mass. So the mass is equal to 10 milligrams. And we know that all of this 10 milligrams is getting into the systemic circulation. We're trying to solve for the concentration of the drug. And here we're just going to assume that this drug is staying within the plasma. So the volume here is 2.5 liters. And so we remember our most important equation. Concentration is equal to mass over volume. And therefore we get a concentration in the plasma of 10 milligrams over 2.5 liters. And we get something about 4 milligrams per liter. And so let's say we were going to graph something like this. What we're doing is we're giving a fixed amount of drug into a fixed volume of fluid. We're assuming no distribution, it's not going anywhere, it's not getting metabolized, it's not getting excreted. The concentration in the plasma would essentially go up, and it would stay the same over time. Now this is the most simplified, unrealistic version, just to give you a sense of what's going on. But let's dig into this a little bit deeper. So here we have two different examples. In example number 1, we're giving a drug by mouth, and we're looking at this plasma concentration as a function of time graph. And in example number 2, we're giving this drug via IV bolus, so into a vein all at once, and we're looking at this concentration as a function of time graph. Now, before we jump into this, I want to just point out the most important concept here that you should walk away with, and that is the area underneath the curve on the concentration versus time graph is proportional to the amount of drug absorbed. So the larger the area underneath the curve, the more drug that is absorbed. So we'll first do this bottom example here, because we just did this on the last slide. We administered a 10 milligram dose of a drug via IV bolus. So the mass absorbed, we said, is 10 milligrams, and the volume was 2.5 liters, and remember here we had 4 milligrams per liter. And this is exactly what we're doing. We're administering the drug into a fixed volume. So if I was going to graph this here, at time t equals 0 is where I administer this drug. The concentration rapidly shoots up, and essentially it plateaus, or not plateaus, but it stays flat because it's not going anywhere. So if I wanted to figure out the area underneath the curve here, we've kind of made up some numbers here. We're saying 5 hours has gone by. So on the y-axis, I have about 4 milligrams per liter. We're assuming this is just a square to figure out the area. or not a square. This would be a rectangle. And the amount of time that went by is 5 hours. So without focusing on units here, the area underneath this curve is about 20. Now let's consider this drug given by mouth, PO. Now from 2 lectures ago we did an example with penicillin. We said we gave 10 milligrams of penicillin by mouth, and we said the bioavailability in that case was 0.25. So what that meant was only 25%, or 2.5 milligrams, gets into the systemic circulation. So we said we started with 10 milligrams, we lost some in the stomach, we lost some at the intestines, we lost some at the liver. Remember, this was the first pass effect before that drug gets into the systemic circulation. And so here we only have 2.5 milligrams that got into the systemic circulation. So if I was going to solve for the concentration, the mass absorbed, remember, mass absorbed, 2.5 milligrams divided by 2.5 liters, and thus the maximum concentration I can get is 1 milligram per liter. So let's take this over to my graph. So here at 1 milligram per liter, this is the maximum concentration. But here we're giving this drug by mouth. And so all of this drug is not instantaneously getting into the systemic circulation. We see this kind of curve here. And so important to note is that this part of the graph, this represents drug absorption. That is the process of the drug getting absorbed. Now, if I want to solve for the area underneath the curve, let's assume this is a rectangle again. So on the y-axis, and we're estimating here, we get about 1 milligram per liter. On the x-axis we have time, so let's say that's about 5 hours. And we look at the units here, and we get about 5. So if I took the ratio of the area underneath the curve of a drug given by a particular route of administration, and I divide that by the area underneath the curve of that same drug given IV, well, what I get is 5 over 20, which is 25%. So this is how we actually solve for bioavailability in real life. If we focus down here on the left, the bioavailability of any route of drug administration is equal to the area underneath the curve of that route of administration divided by the area underneath the curve of that drug given IV. So here, for our drug given by mouth, we said the area underneath the curve was 5 for a given PO, and the area underneath the curve of that drug given IV was 20, so we get a total of 0.25, or 25%. And that is this penicillin G example. So, taken together, this is an important concept you should remember. Area underneath the curve of a route of administration over the area underneath the curve IV. Now let me ask you a question. What is the bioavailability of a drug given IV or intravenously? Well, if I do that, the route here is IV, so I would just get 1. So the area underneath the curve IV over the AUC IV would be 1. So by definition, the area underneath the curve, by definition, the bioavailability of any drug given IV is 100%.